All right, everybody. Hello, welcome back. Here we go again. Ready to rock in our geology class. Welcome, everybody. I hope everybody's doing wonderful. We are here to talk about rivers and floods here today, continuing our discussion of the hydrosphere. The hydrosphere, we're looking at the way that water moves because what influences the ways that water moves is oftentimes the geologic conditions that surround it. So we're going to talk about the hydrosphere. We're going to talk about what a small portion of the hydrosphere actually consists of surface water. We're going to talk about surface water movement and how that's a really dynamic process, how the movement of surface water absolutely can change the landscape and can do so dramatically over relatively short amounts of time. And then we're going to talk about how we describe and define different types of rivers and the water that moves within them and all of that really fun stuff. I'll note that this lecture topic is really fun because, like volcanoes, rivers absolutely can act fast. They can change the landscape fast. And, we oftentimes see these rivers that are channelized and seem like they've never moved at all over the course of our lifetimes, when in reality, in nature, rivers move quite a bit. And they absolutely have carved and shaped and deposited sediments that define our landscape today. So it's a ton of fun. I'm excited to share this stuff with you guys. So here we go. Let's take a look at the hydrosphere. Again, the hydrosphere, that aspect of the Earth system that is water, right? Hydrosphere, that all that water, the majority of that water, right? The majority of that water, more than 70% of the Earth's surface, nearly all of the water in the world is contained in the ocean. So more than 97% of the water in total, right, is in our oceans, right? Covering a huge portion of our planet. The small remaining sliver there of freshwater, non-ocean stuff, the majority of that is, again, that's glaciers. Then we've got a bundle of groundwater out there, and then we've got a bundle of water that's stored in soil moisture and in our atmosphere. But then there's a small fractions of percentage that exists in our surface water as freshwater lakes, saline lakes, inland seas, and in our streams. Okay, so again, a really small piece of the overall pie, but still a lot of water to be dealing with. And so when we talk about the hydrosphere, we're talking about water moving through various elements of this pie chart, right? That is, water from the ocean fuels a lot of the precipitation that we see on land. A lot of the precipitation either runs back off into the ocean or infiltrates into our groundwater supplies, or in some cases is even evaporated and circulated back into our atmosphere, right? So these water molecules are moving in and among each of these systems, each step along the way, each change in the state, the physical state, and the location of this water has a direct impact on things like weathering and erosion, the distribution of life on this planet, and the shaping of the surface of this planet. All right. So again, this lecture, we're focusing on surface water, largely surface water in rivers and streams. So what is a river or a stream? The definition of a river or stream is simply water flowing at Earth's surface in a confined channel. So water moving in a confined channel. So we obviously we look out there and we see there's a whole bunch of different rivers that have different characteristics to them, right? You go down and you visit the Colorado River. That's a very different river than our namesake Santa Ana River here in Riverside. Right? It's a much bigger river. It flows differently. So what are some technical terms that we can apply to describe some of those aspects of the rivers that we're sensing as being different, and very much are? Well, the first thing we describe is gradient. Gradient is just the slope of a stream. Gradient can either be very steep or very shallow. And gradient is calculated just by looking at it like you would any gradient. It's just rise over run. Right? That is, what's the change in elevation, right? What's the change in elevation in a stream? So that's the rise. right? Over what distance? That's the run, right? That's how you calculate gradient, right? It's just rise over run. How much elevation change over what distance, right? And so the gradient of a river can change along its entire course. You can describe small sections of gradient along the course of a river, or you can describe the gradient as a whole, right? But gradient, again, the steeper the gradient, the faster that water is going to flow. The more shallower the gradient, the slower it's going to flow. Competence and capacity both describe what the sediments that a stream is capable of carrying, albeit from two different aspects related to those sediments. Competence describes the largest sediment grains a river can carry. In general, if you increase gradient, the river will be able to carry larger and larger sediments. So if you increase gradient, you increase competence, right? You increase gradient, you increase competence. You can carry really large boulders if you have a steep gradient. Capacity describes the maximum solid load a stream can carry. So that typically, when you see rivers with a high capacity, you're going to see that oftentimes the water is a little bit murky, and that's because inside of that murky water are a bunch of solid materials that river is carrying. And so the Mississippi River has a high capacity. It carries lots and lots of solid load because it's moving a tremendous volume of water. All right. So what's the mission for a river? Why do we have rivers? Well, we have rivers because of plate tectonics. Again, as we've said throughout the semester, plate tectonics takes land and lifts it out of the ground, right? Giving that land potential energy. Gravity wants to flatten the earth out, make it water world. But plate tectonics, fortunately, acts more quickly than weathering and erosion. So we see these areas of high topographic relief. So what rivers are doing is the work of gravity. Rivers and streams are taking that landscape, and through the movement of the water, they're taking those materials. As we talked about when we discussed weathering and erosion, water is a big agent of both weathering and erosion. So it's taking those materials, it's breaking them down, and then transporting them to the ocean. Ultimately, what that water is doing is it's moving from points of high elevation to low, what we call base level. Base level. We talked about base level during our previous lectures, but I'll mention again that base level can be ultimately the ultimate base level, again, is the ocean, right? But we can have local base levels as well, things like lakes or small basins, those sorts of things, right? So ultimately, that's where rivers are moving from points of high elevation to these lower elevation base levels, bringing sediments from high elevation to low. This is a figure demonstrating that here we've got geology creates this layer. There's this layer of rock, this resistant layer of rock that creates a cliff or a bluff there. There's waterfalls flowing over the top of that bluff that help to erode it. And as they erode that resistant bed, it chases backwards. That erosive capacity of the water is seeking to eventually flatten out that landscape. And that's exactly what happens. Every sediment moved by this river is one that chips away at the topography over which that river moves, right? And that material, again, transported back in the ocean, where eventually it might be recycled, again, because of plate tectonics. We can have these artificial base levels as well. The installation of dams, reservoirs, absolutely adds a new base level. And sediments from these rivers will make their way to these reservoirs, and clearing out those sediments due to erosion from these rivers and deposition from these rivers is a big deal in some of these reservoirs that have these high capacity streams entering these reservoirs. And so again, base levels can change. We can make artificial base levels, but ultimately that's what rivers are doing, is they're taking these materials from high elevation to low. Waterfalls, again, are local base level conditions and oftentimes present local base level conditions, right? Waterfall is where the water is collecting and then suddenly falling over these cliffs. So that's, and again, another opportunity there for that water to collect there, deposit some sediments. and really limit the water's ability to erode those materials deeper. But there is erosion that obviously happens at waterfall. That's evident in this picture here, where you see all these rocks here in the foreground, right? There in the foreground, that's evidence of the waterfall eroding. And when the waterfall erodes, it will continue to retreat backwards, just as we saw in this image here, is that as erosion takes place, it's taking place in this direction. So that waterfall is moving its way backwards. And it does so through a process called nick point migration. Nick point migration is how a waterfall moves. And so what happens is you've got maybe this resistant, we're looking at Niagara Falls here. You've got this resistant layer of dolostone, right? Of dolostone, essentially slightly altered limestone. You've got this resistant layer of rock over which the water flows. It's preventing any erosion here. So what ends up happening is when that water goes and crashes into the pool below, what it starts to do is it starts to chip away at the less resistant mudstones and shales. And in doing so, just like we saw along the coast with our breaking down of our sea cliffs and things at our coast by chipping away at the base of those cliffs, we see that here at the base of our waterfalls as well. Chipping away at these materials cuts away the support of those overlying rock units to eventually the point that they fail, right? You get a mass wasting event maybe where you get these big blocks breaking apart, and that waterfall again will start to move its way backwards upstream and will continue to do so until again the limits of that resistant rock layer are reached, and then that waterfall will flatten out a bit through time, et cetera, et cetera. All right, so that is nick point migration. And again, always, the waterfall will move upstream, right? And that's because, again, we're eroding these materials as we're moving them upstream. All right, let's take a look at some of the main features involving a stream. And we're going to see that it's much more than just the confined channel that the water runs in. We talk about rivers as a system. We're talking about not just the river channel, we're talking about all of those areas surrounding the river as well. So the river or a river may wind its way back and forth across a valley floor, and in doing so is serving to erode and deposit sediments as it makes this route back and forth across the valley floor. So as it's doing that activity, again, it's both eroding and depositing sediments along what we would call the floodplain. The floodplain is that area that when that river floods could be potentially covered in water from that flooding event. So within the floodplain near the river channel, right, we're going to find really coarse-grained sediments. Outside of the river channel and other portions of the floodplain, where that river channel is occasionally overrun by water and that water seeps out into the surrounding environment and then deposits those sediments are generally going to be finer grained sediments. And they're actually really great sediments for growing crops. Nutrients will come with these sediments as well. So oftentimes in these floodplains, that's oftentimes where you'll see some agriculture happening as well. That's also because development in the floodplain is oftentimes something to avoid those developments being flooded. Also on the margins of our river channel, because during those flooding events, sediments are deposited right next to the river channel first, you start to develop these natural levees, these little raised levees next to the river channel there. Sometimes next to the main river channel, you'll have another river channel running parallel to it, much smaller, but running right along with it. We call this a Yazoo tributary. That's what this parallel running river is a Yazoo tributary, okay? Here in this floodplain area, where we get this flooding and where those flooded areas may stay pretty consistently wet, that'll sometimes be referred to as a back swamp. And constraining this entire system, right, is oftentimes geology. oftentimes small mountain ranges or exposed portions of bedrock that define then the valley wall, Okay, so this is a three-dimensional view of that arrangement. Here's a two-dimensional view of that arrangement. So here we've got the river channel. Here we've got our natural levees and our back swamp back here and our Yazoo tributary. But there's one new feature that we're seeing in this image, and that is right here, these little flat spots called terraces. Again, as rivers move their way back and forth across the landscape, they are carving sediment and depositing sediment as they do so. When the river flow is high, generally the erosive power of the river will go up. And so rivers, when you take the velocity of the river and you increase it, maybe there's a period of some climate change that results in increased precipitation, so increased flow of the river's increased flow will result in it having a higher erosive capacity. So it'll actually take the old surface that it used to migrate across and cut down into it. And when it does that activity, what it'll leave behind are remnants of the former surface of the adjacent floodplains. And that's what we see as these terraces. So in these terraces, we have our oldest terraces are those that are at the highest elevation, and the lower terraces get increasingly young, right? So we get newer and newer terraces as we approach the river. And here where we have the back swamp, this would maybe be the next terrace. If this river picked up velocity again and started cutting downwards, we might form a new terrace right here. So again, the presence of these terraces gives us some indication of changes in the flow of the river, and can be utilized for things like climate reconstructions and all sorts of things. If you find like datable materials on a terrace, you may be able to say something about when the velocity of the river might have changed. And maybe you correlate that to things that you've seen in other parts of the world related to climate variability and potentially make a story there, right? Super cool stuff. All right. So how do streams flow? Right? How do they flow? How do we describe the flow of the water in a river, right? That is, there are two main types of flow of water, right? That's laminar flow and turbulent flow. This is a picture of a Grand Canyon expedition there experiencing some turbulent flow, right? You see this in waves at the beach, right? That turbulent flow, the white water rolling up on the beach there, right? Versus laminar flow. Laminar flow doesn't have that same chaotic element to it. It is nice and clean, right? Might be moving fast, right? But it doesn't have that chaotic element to it. It's somewhat predictable. So flow within any river can be laminar or turbulent, right? And so you can have turbulent flow in a very shallow river with very little water in it. You can have laminar flow in a very big river that has a lot of water moving through it, right? So the nature of the flow is primarily dictated by the speed or the velocity of the river in association with the river's depth, okay? So if a river maintains its velocity and the depth of that water changes, if the river becomes much shallower at the same velocity, you might get some turbulent flow. If the depth of the river deepens, that turbulent flow may turn to laminar flow again. So again, when you look at a picture like this, what this likely indicates is high velocity in this river, right, in a relatively shallow portion of the river. And that's why you can go on these sorts of expeditions along the Colorado River here and experience times where the water is very tranquil and calm, maybe in deeper portions of the river or wider portions of the river. Whereas in narrow portions of the river where the water starts to move faster, or in shallow portions of the river where that water is moving faster over a shallower area, you can experience these sorts of rapids, right? So a lot of it, again, comes down to velocity in association with that water depth. All right. So if we wanted to take just rivers and streams as a whole and divide them into two general groups, we could do so. And we would divide those into either braided or meandering streams. Braided or meandering streams. In general, oftentimes streams have both braided and meandering elements. That is, the braided elements of the stream, are typical of those areas that are near the headwaters of the stream. That is, near the mountains where the stream begins, right? So we're talking about high velocity streams that don't have a single stream channel kind of organization, right? Braided streams have multiple channels that feed into each other. They may crisscross, right? That's the term braided, right? They're braided with each other. Whereas a meandering stream generally lower energy. Usually this is in areas where the stream gradient is a little bit lower. We'll see that those collection of channels will organize themselves into a single channel that somewhat meanders across the landscape, right? So again, the type of stream might vary over the course of a stream. So braided streams can become meandering streams, but the type of stream that we have in any given area is really related to the proximity of that stream to the headwaters. That is, the further we are from the headwaters, right, the more likely we are to have a meandering type stream, right? Those headwaters, again, is where the stream begins, right? That initial collection area for that stream. So let's take a look at this profile of a stream. And again, we see near the headwaters here. So here's where the stream begins. We have many channels coming out of many canyons that all start to coalesce and do their thing, crisscross and all sorts of stuff in this steep gradient area. Many of these stream channels in this area are going to be of the braided type, right? That crisscrossing stream type. Whereas as you move out along the longitudinal profile of the stream into this more gentle slope, this gentle gradient area, we see that those channels, they come together, they collect into a single stream channel that then meanders through the landscape, thus a meandering stream, okay? So again, this is a pretty typical pattern. This is a pretty typical pattern for streams, but there are some additional drainage patterns that are a little bit of a one-off and are related to the geological conditions in that area. That is, if we have, let's imagine we have a network of canyons within a pretty rugged landscape. Where you have a stream channel, maybe there's a fault that cuts through this mountain range. That's a relatively straight feature, but surrounding that fault are a series of canyons that feed into or point toward that structure. That produces this kind of tree-like pattern, right, in this stream channel network. That's what we call a dendritic drainage pattern. Volcanoes have a unique drainage pattern in that the water flow along a volcano radiates out from the top of that cone, right? So all the streams are somewhat pointed away from each other in this circular pattern. This is what we call a radial drainage pattern. In areas that are heavily jointed, where joints form the predominant geologic features in the landscape, maybe an area that's been heavily fractured, we can actually have these streams that make these right angle turns. If you have a good resistant rock that's heavily jointed, streams can make these right and left hand turns here across the landscape in this very squared off 90-degree type fashion. We call this a rectangular drainage pattern. And again, that is going to be something that typically is going to be a joint-dominated landscape. And then in areas where maybe we have some folded or dipping resistant rock, right? What we might see is that between those layers of resistant rock, right, are some low valleys, right? Repeated low valleys. Those low valleys will each have their own drainage system within them. And those drainages may connect to a main drainage that cuts across some of those resistant rock layers. You might notice that this resembles the way that, if you've ever seen the way that they grow grapes, right? Or some other vegetables, they grow this way too, where they take the leaves and the stems of those plants and they stretch them out along what is called a trellis. Those of you that garden might be familiar with the term trellis. This is known as a trellis drainage pattern because it looks like kind of like how you would grow a grapevine. All right. So these, again, are some unique drainage patterns, but this is the typical drainage pattern where we've got this braided portion here near the headwaters transitioning into this meandering portion further away. All right. So obviously streams, they come in different sizes, different magnitudes, right? And a lot of that is dependent on the size of the drainage basin and the number of streams that feed into that system. So this a drainage basin is any area where all the water that falls in that area will drain into the basin. And so ultimately, near the headwaters of that basin, you're going to have relatively small streams that are going to feed into bigger and bigger streams. And this is what we call the collection of this increasing magnitude of streams. We call that stream order, which is the measurement of the relative size of streams within that drainage basin. And so what you're seeing here within this little drawing of the stream system is up here near the headwaters, we have a bunch of what are called first order streams, right? These are all first order streams. What we get here, or what ends up happening, is those first order streams combine to make second order streams, right? So we have some second order streams there that are the combination of a couple first order streams. If you have two second order streams, the combination of those two second order streams, they make a third order stream. So notice that this second order stream and this first order stream, they combine right here, right? They combine, but they don't change the stream order for this segment of the stream, right? Rather, it takes another second order stream to increase the stream order for this second segment of the stream, right? So now we've got some third order streams here. We've got 2 and 2. This third order stream here, now combination of 3 and 3, raises the order of the stream again to a fourth order stream. So this main channel of this drainage basin is a fourth order stream. So why don't we go ahead and do one of these stream ordering exercises together? Because hint, hint, this might be something that comes up at some point in this class, say in a future quiz or exam or assignment. So let's go ahead and I'm going to draw in a stream, and I'm just going to do so somewhat randomly here. I'm going to draw in a drainage basin stream network thing here. All right. And this is completely random, and you could practice these sorts of random drawings on your own as well. So there we go. I've got myself the stream network within a drainage basin taken care of. So the way you do this stream ordering exercise is you start on the outside of your network. Our goal here is to label every single segment and every individual segment on this diagram with a stream order. And so we start from the outside and we work our way in. So starting on the outside, we identify all of those first order streams, those streams that don't have any other streams feeding into them. So here's one, here's another one, this is another one, here's another one, here's another one. This little segment right here, yep, that's another one, that's another one. There's one, there's one there, there's one there, one there, one there, one there, and one there, right? So just all of those streams that don't have any other streams feeding into them, right? That's all of these outermost branches. And it looks like I missed one right there as well, right? So no streams feeding into above these streams there. We know this is upstream too, because we see these V's, right? These V's right here where the stream channels come together, they're always going to point down gradient, okay? Always going to point down gradient. Okay, so we labeled those first order streams. Now let's go through and label the second order streams. And so we increase the stream order every time we go up in stream order by 1. All right. We go up in stream order by 1 every time we see equal stream orders meeting each other, right? So here we've got 1 and 1. Those come together. So this little segment of the stream right there is a 2, right? And we can go through this entire rest of this branch here. So 2 and 1, we just pick the higher of those two numbers. We don't go any higher than 2. We pick the highest of those two numbers. So then we've got 2 and 1 again. We just pick the highest of those two numbers. And that's all those segments on the branch. So you want to make sure that you get every single one. Make sure you're not skipping any, because that's a pretty common source of error, would be to like miss this little segment right here. Okay, so now we've got 1 and 1 here. So this one right here, this long segment right here, well, that must be a 2. Here we've got 1 and 1 here, so this must be a 2 as well. Here we've got 2 and 1, so you guessed it, that must be a 2 as well, right? And so now we go back up here. Here we've got 1 and 1, there's a 2 there. Here we got 2 and 1, so this little segment right here has to be a 2. Here's 2 and 1 again, so this has to be a 2. 1 and 1 there, so this has to be, once again, a 2. All right, so now we're done with the 2s. Let's move on up to the 3s. All right, so now we can move into some of these main portions of the trunk here. So 2 and 2, that makes a 3. Right? So this segment right here, from this point to this point right there, is a 3. So now we have 3 and 2 right here. For this little segment, we got to capture that little segment right there. So we go ahead and we do that, and that little segment right there is a 3. Right? That little, you got to get that. Those things can be sneaky sometimes, but you got to account for them. 3 and 2 here. So this little segment right here, yep, you guessed it. That must be a third order stream. And then we've got 3 and 2 here. So this final segment, that too must be a third order stream. So the largest stream channel, the main stream channel in this diagram that we drew is a third order stream. That's how you do stream ordering. And so maybe on a quiz or an exam, I give you a diagram like this and I ask you, what's the highest stream order in this diagram? Or maybe I say, what is at this location, what's the stream order? So you definitely want to be able to do this exercise. So if having any trouble, again, that is what I'm here for. I'm more than happy to help with this exercise. All right, it's a really good one, one that commonly pops up again on quizzes and exams. All right. Well, let's keep on rolling then. Let me get our lecture slides back. All right, there we go. All right, so again, the magnitude of the stream orders and the magnitude of these headwaters, it's a scale-related issue. You can chase the headwaters for some of our larger streams all the way across state lines. And in fact, the Continental Divide, right? The Continental Divide, which cuts through New Mexico, Colorado, Wyoming, Montana, Idaho, defines a line defined by the topography of our state, upon which a drop of water that falls on the east side of that line is going to flow to the eastern portion of the United States. Maybe that's down towards the Gulf of Mexico or towards the East Coast, right? But a drop of water falling on the west side of that line, it's going to flow to the west. So this divides North America into these two significant drainage basins. So you may have heard of the Continental Divide at some point in your life's travels, and that's what's being referred to here, are the drainage basins and the headwaters associated with water movement being divided along this line through much of North America. All right. So ultimately, if you wanted to do your stream order exercise, you could chase back those stream orders all the way back, potentially in some cases, to this continental divide for rivers like the Colorado River, right? Or the Mississippi River, right? Fun exercise. All right. So streams, one of the things they're doing is they're carrying sediment. And if you've ever gone to the river, you may notice that, well, I feel there's sediment moving along the bottom of the river and there's sediment moving within the river. And that is very much true. And there are also different ways in which that sediment moves in either of those settings. The sediments that are being carried by the water that do not contact the bottom of the river, that's what we call the suspended load, the suspended load. The suspended load consists primarily of silts and clays, the really small stuff, the stuff that makes that water murky is being carried in suspension and will be carried in suspension all the way potentially to the oceans. Those materials that interact with the bottom of the river channel, we call that the bed load, and that's going to consist primarily of our sands, our gravels, our pebbles, our cobbles, our boulders, the larger sediment grains. And in that bed load, sediments can move in a variety of ways. Some sediments, large sediments, might just roll their way along the bed of the river. Some sediments may slide their way along the bed of the river. These are terms that are pretty self-explanatory, a rock rolling or sliding. But sometimes sediments, it's almost as though they're bouncing along the bottom. That is, they'll get picked up by the current, they'll move with the current over some distance. Sometimes that distance can be pretty great, but over some distance to where that sediment will come down and come into contact with the bottom of the river channel again, and may come to rest for a little bit until that current again picks that sediment up and takes it to its next location. We call that movement saltation. And that is typically the movement associated with the movement of sand within a river channel, right? Is through that saltating movement like that bouncing along the bottom of a river channel. Let's look at the flow of water inside of a river. You may notice if you sit on the margins of a river, which is an awesome thing to do. I don't know if any of you guys have a chance to go visit the river and hang out. It's fun. But sitting at if you do, I'll encourage you guys, next time you're sitting at the river, you look out in the river and you'll see that water's moving very quickly. It's carrying boats, and water skiers, and all sorts of stuff, animals down the river very quickly. But if you look right at where you're sitting, right at the edge of the river, that water looks as though it's sitting exactly still. It looks like it's just sitting there, right? Exactly still. And that's because there's a whole bunch of friction in that very shallow water near the shoreline. Water flows at different rates within the river, right? Different velocities, which means that across the width of a river, there is what's called a velocity gradient, where the maximum speed of that river in a straight line segment of the river, so no twists and turns, the river is just moving straight, the maximum velocity, the highest, fastest moving water will be right in the middle of that river, just below the surface. That's where friction is at a minimum, right? And so the water moves the fastest, okay? And so the speed at which that water is moving in that maximum velocity zone, right, depends on the depth of the river, the width of the river, that can take some of that velocity and dilute it out, right? Or I should say the steepness of the gradient varies based on those conditions, right? That a wide river, right, the gradient is going to be much more gradual as you move towards the middle of the river, whereas in a narrow, deep river, you're going to see that the velocity changes very quickly, which is an important thing in that if you're standing on the margins of a river, a really powerful river, standing there, you might think, oh, the water's not moving too fast. I bet I can swim across this. If you went to swim across it, by the time you got into the middle of the river, you might be moving really, really fast, right? And that can present some dangerous situations as well, right? And again, that's because of this velocity gradient, where that velocity is fastest right in the middle of the river. But the velocity of a river also changes along the length of its flow. That is typically, as we mentioned earlier, near the headwaters of a river. Near the headwaters, that's going to be the steepest gradient. That's generally going to be where the water moves the fastest. That's going to be the highest velocity zone. It's going to be your highest energy zone is near that headwaters. As you move out towards the floodplains where that gradient gets less steep, your velocity will lower as well. Velocity of a stream is typically measured in meters or feet per second. Oftentimes here in the States, you'll see the velocity of a river measured in FPS. That's feet per second. Sometimes this information is provided for rivers. Sometimes people that like to fish in rivers and streams rely on velocity reports, as it's really hard to fish sometimes in high velocity or high flowing water. And that's what they're doing. And so oftentimes that velocity measurement is kind of an average across the stream, because again, you might have a zero velocity along the margins of that river, but then in the middle of that river, you might see that that river is moving very quickly. All right. All right. So let's just take a moment to enjoy a picture of a river, right? We've seen lots of drawings, but here's a beautiful picture of a river. And what do you see? Well, I see a beautiful landscape and a forest, maybe just after the fall. Looks like the leaves have come off the trees, right? Let's take a look at the sediments, right? What we see here is that this river is bending through this landscape. And if you look closely along this bank on the opposite side, you'll see that it's very steep, right? There's a little steep cut bank there on the opposite side of the river. Whereas on this side, you have a more gradual slope and you have all these kind of loose sediments just sitting there. The reason for that is that a river not only changes velocity from the margin of the river to the other side, right? But the gradient, the velocity gradient, changes its shape as the river twists and turns across the landscape. That is, as this river is making this turn, right? As this river is making this turn, what ends up happening is for this water to be able to keep up with itself, the water on the outside of that turn, it speeds up. Whereas the water on the inside of this turn, to not outrun its fellow water particle colleagues here, slows down. And as we learned when we talked about sediments and weathering and erosion and sedimentary rocks and all that fun stuff, we learned that energy, right, is related in part to the speed of which the water moves. And the faster that water moves, the more erosive capacity it has. So as this water is speeding up on the outside of this bend here, it has some increased ability to erode these materials. Whereas that water is forced to slow down on the inside of the bed or of the bend here, now it is forced to deposit those sediments. So velocity changes as a river twists and turns across the landscape. And on the outside of these bends, the river speeds up, which makes these environments erosional environments. These are erosional settings. On the outsides of these bends are where erosion is going to happen. Whereas in the inside curve of a bend, the river slows down and you get some sediment deposition. And if you're thinking to yourself, well, Savinfield, if the river is cutting outwards and depositing inwards, doesn't that mean that the river will like change its location and kind of move towards the outside of the bend? And I would say to that, absolutely, you nailed it. That's exactly right. And that's part of the dynamics of a river, is that they move, that river channel moves through both of these processes of erosion and deposition. It's super, super cool. So factors affecting then erosion and deposition, the ability for a stream to erode and or deposit sediments, include obviously the speed of the water moving through it. The shape and the size and the roughness of that channel are going to influence the friction experienced by the water that's moving through the river. And then discharge, how much, what's the actual volume of water that is moving through this system. So what happens then? Let's talk about this depositional aspect of a river, right? What happens as this river loses steam? What happens as it slows down and starts to deposit things? Well, it starts to build structures that are mostly composed of loose sediments, what are called channel deposits, point bars, or what are called deltas. So in this image, we have, again, a meandering portion of this stream. You see this stream kind of winding its way, absolutely beautiful picture, this stream winding across this landscape. And so on the outsides of these turns, again, that water is speeding up. It's trying to erode the outside of this bend. But then look at on the inside where this sediment or where this water is forced to slow down, look what it's doing. It's depositing all of these sediments. And these deposits of sediments, they will continue to grow outwards and outwards along with the erosion that's happening on the other side of the channel. These little structures right here, we call them point bars. Those are called point bars, and they will always be made on the inside of the bends of these stream channels. So these point bars will always be made on the inside of the bends of these stream channels. That's where these point bars are going to be deposited. So these point bars, along with then this erosion, right, is resulting in this river moving across the landscape. On the erosional side, on the outside of these bends, counter to our point bars where that erosion is taking place, we call that a cut bank, a cut bank. So as these cut banks are being made and these point bars are being deposited, that river's location is constantly changing. So much so that sometimes these meanders in these rivers will actually, sometimes they'll connect. That is, there are lobes of these rivers that will get completely so contorted by the creation of that point bar and the erosion along the cut bank. They get so contorted that the river eventually goes, you know what, I'm kind of done taking this long route. I'm just going to go ahead and take the shortcut. And maybe a big rain event or something allows it to break through this narrow area here called a neck. And when that happens, water will actually remain in that former river channel for some amount of time. It'll remain there. It'll be essentially a lake. We call these lakes oxbow lakes. You may have seen an oxbow before. You may have seen pictures of cattle with the kind of horseshoe-shaped item around their neck. That's called an oxbow, and that's what these lakes resemble as well, is that oxbow structure that cattle sometimes wear. And so these oxbows are the cutoff meanders of these rivers. If you take a flight, particularly across the middle portion of North America, you are likely to fly across some of the plains where you're going to see some of these big meandering streams. And you can look for these little oxbow lakes. There are several of them in this image. There's one there, there's one there, there's one there. And these oxbows, again, here's another one here, show the former locations of this river, right? You can really see how much this river is cut across the landscape. And again, I encourage you guys to keep an eye out for this next time you're on a flight across the country there. It's kind of fun to try to pick out the oxbows, because you can really see how dynamic of an environment rivers can be in those landscapes. So again, these things are weaving their way across, they're cutting their way down and through sediments and depositing new. And as a result, as we mentioned earlier, you can create in the floodplain these terraces that mark the former locations, the former elevations of those streams. So here's a model diagram or series of diagrams showing the formation of these terraces. here in A, we've got this meandering stream cutting across the landscape there. Maybe something happens, the flow of the stream picks up, so it really starts to down cut through these sediments here, leaving behind the former floodplain in the form of this terrace. We have, again, maybe a climate-related event that precipitation really goes up, so we start to cut down through those terraces again. And so now, again, these higher elevation terraces represent the older floodplain surfaces, right? Getting progressively younger as we approach the current existing floodplain. So these terraces sometimes, again, important for like climate reconstructions and those sorts of things because they're related to the flow of water through the stream channel. All right, here's a really fun picture of some of these necks and maybe some potential oxbow is going to form in here if we get this stream or this river here to bust through these necks and cut off those these long ways here in the flow of the river. Here's an interesting application of some of this, maybe to your life, and that is if you identify, or if you're looking at these rivers, you can identify the cut banks pretty readily. And what I want you to note is that erosion along the cut bank can take course. Significant amounts of erosion can take course over the course of just hours, if not maybe days. Large scale flow events inside of a river can really result in that river being able to chip away at its margins. And so houses, infrastructure installed along the margins of a river, particularly near the cut bank, are particularly susceptible to impacts from those erosional processes. That is, you can see this house is about to be lost as the river is encroaching on it. So sometimes what you'll see along the outside of these bends, you'll see the installation of large rocks and boulders that are designed, those big rocks and boulders are designed to prevent erosion. That is, it takes a lot of energy to move them. So you put those in the way of the river and they really aren't able to move the sediments that are behind them. This material that you put in place to protect these cut banks, sometimes referred to as riprap. If you go down along the Santa Ana River, near some of the parks that line the Santa Ana River, you'll see riprap installed along the margins of that river, particularly along that cut bank, that outside of those bends in the Santa Ana River. It's kind of a neat thing to notice. All right, so again, rivers, they move. Right? They are moving and they move by meandering. So they move left and right through the deposition of these point bars, through the cutting of these cut banks, but they also move up and down related to the amount of water that's moving through them. You increase the velocity of the river, you make it flow faster, and it's going to start cutting down into the existing floodplain sediments. So I hope I'm painting the picture for you guys that rivers, these environments that surround them, can be really complicated and are constantly going through a state of change as a result of both these patterns of erosion and deposition. Rivers also migrate upstream. Right at near the tops of rivers, rivers might migrate their way upstream. That is through erosion, very similar to our process of nick point migration. Those rivers may have erosion right at the headwaters that results in these streams colliding with one another. Or maybe the meanders of a stream get such that a meander cuts all the way over into another stream. When that happens, that's called stream capture. And that can be a potentially dangerous thing if you have a relatively low order stream and a high order stream captures that low order stream, combines with it. Those areas surrounding that low order stream suddenly will experience a high increased, a high level of flow within that stream channel quite suddenly. Right. So again, during storms and things where water is moving around and actively eroding and shifting course and doing all of these things, really those surrounding areas are vulnerable to considerable change too as a result of something like stream capture, right? So again, during these events, when you hear about flooding and those sorts of things, what we're talking about are hazards that are really unpredictable and can put a lot of people at risk that wouldn't have really assumed that they otherwise would be, right? Streams running into each other are one way that we are exposed to hazards of increasing the velocity and volume of water that's moving through a stream. That can happen quite suddenly. All right. So a lot of what we've been describing, velocity of water, right? So when you look at, if I were to give you, let's say a rain gutter, right? Just a narrow rain gutter. And I were to make that water move just as fast as that water moving in the Colorado River, right? That water moving through that rain gutter is not going to have nearly the same amount of energy, the same scale as what we see in the Colorado River. That's obvious, right? So it's not just about velocity. It's also about the volume of water that is being moved through these streams that makes them different from one another. And that's what we describe as discharge. Discharge. Discharge in a stream is a measurement of how much the river is outputting, how much water is moving through the river. And it's typically measured here in the States in cubic feet per second, CFS. This is another number that you'll commonly see reported for different streams. CFS. In other countries, it may be cubic meters per second, right? But here in the States, we oftentimes see it as CFS, cubic feet per second. So a measurement of how much water is coming out of the river. So we need 3 bits of information in there to calculate discharge, right? That's the velocity, how fast the water is moving, the depth of the river, and its width, okay? So the depth, the width, and the velocity, right? So velocity and cross-sectional area is another way to think about that. Because what we're measuring, what we're going to imagine is that we have, let's say we have a little box that we've made out of maybe PVC pipe or something. It's a little box that's about 1 foot by 1 foot, right? It's a 1 foot by 1 foot square box. And what discharge measures is how many cubes of water, 1 foot by 1 foot by 1 foot cubes of water would move through that box every second, right? How much water would move through that box every second. So let's go ahead and do this exercise. Let's imagine that we've got a river that has a velocity, right? Velocity, let's say it equals 10 feet per second, right? So velocity, that's a rate, right? Distance over time. 10 feet per second, that would be our velocity. This would be a given, right? This is what we would give you. A depth, let's say, I said the depth of the river was let's say at its deepest point, we'll just use its deepest point. We'll say the depth of the river is 5 feet. Let's say the width of the river is maybe 20 feet, right? And then if I were to ask you, well, what is discharge? What's the discharge of this river? Well, that's quite simply then 10 feet per second times 5 feet times 20 feet, right? So 10 times 5 is 50, times 20 is 1,000. So the discharge equals then 1,000. We've got foot times foot times foot, right? So that's cubic feet, right? And then we've got this little per second to account for, right? So cubic feet per second, exactly what we see up here, right? So the discharge of this river that's moving, the water's moving at an average velocity of 10 feet per second. The river's 5 feet deep and 20 feet wide. That has a discharge of 1,000 cubic feet per second. So that means that in that 1 foot box, right? That 1 foot box, 1,000 blocks of water, 1 foot by 1 foot by 1 foot blocks of water are flowing through that box every second. That's what discharge is describing. And these numbers, you see them, they're really high, and it's amazing to think about that volume of water moving in these rivers. And that's what's being described here. Okay. So again, questions that you might see on this, say in a quiz or an exam, would be, you have a river with a velocity of 5 feet per second, a depth of 5 feet, and a width of 100 feet. What's the discharge? And again, you would simply multiply those three numbers and add on cubic feet per second, and that is your answer. All right. Again, we're describing, again, how much water the river is outputting. All right. That's discharge. Okay, so more significant rivers are going to have more discharge. Less significant, lower order streams are going to have lower levels of discharge. All right. All right. Awesome. All right, let me clear this here. Okay. All right. So back to these terms, competence and capacity. Competence and capacity, and how that relates to discharge and velocity. Again, as a reminder, competence, the largest sediment grains a river can carry. And in general, you increase the gradient, you increase the competence of a river. So the steeper rivers, they can carry larger and larger sediments, whereas when you get out in the flatter areas, lower competence, only capable of carrying maybe sands and clays and silts and things like that. Capacity, the maximum solid load a stream can carry. So the Mississippi River has a high capacity. And what we're going to see is that capacity is actually related to discharge. As competence is related to velocity, again, we increase the speed of the river, we increase the size of the sediments that stream can carry, right? So even a very small stream that's maybe only a few feet wide, if it's moving across with a steep, along a steep gradient, right? A really steep area, we can see that water racing down along that landscape. It's capable of moving very large sediments, boulders, cobbles, pebbles, right? So that's velocity. But discharge, the overall amount of water that is moving through the system that the river is outputting, that discharge, right, increases the capacity of the stream, the maximum solid load that stream can carry. So what oftentimes happens during flood events, is that both the discharge of the stream goes up and the velocity of the stream goes up, which increases both the capacity, the solid load the stream can carry, and the size of the stuff that the stream can move. And that's when we get these big erosive events that absolutely can change the landscape overnight. The power of that water is enhanced, and it can absolutely tear through the landscape and leave an entirely different looking landscape behind. That's why floods are so dangerous, is because, again, during these events, velocity is going up, discharge is going up, so capacity and competence, they're going up as well. All right. So rivers are making their way again to base level. And as they make their way to base level, or when they finally get to base level, their velocity is forced to change dramatically. That is, where rivers meet the base level, right, where they meet, say, the ocean, the current of that river as it meets that big open landscape of water, all of that energy is diluted into the ocean such that the river slows down. And when the river slows down, all of that stuff that it's carrying, right, all of those sediments that are being carried in its suspended and bed loads, all of that stuff is dropped because the energy is not there to carry that stuff anymore. So we end up creating these landscapes. We end up making these structures that are characterized by the relative change in velocity that's experienced by these rivers as they enter the sea, in association with ocean dynamics that are occurring with relation to tides and waves and those sorts of things. So deltas, we get these really neat and unique environments where freshwater systems are meeting marine systems, resulting in these really unique landscapes. And so we have these so-called deltas, these deposits of sediments that reflect both dynamics that are going on within the river as well as dynamics that are going on in the ocean. And we have three main types of deltas. Okay, the first type is a river-dominated delta. River-dominated deltas, generally, they extend themselves out into the sea. That is where you have high discharge streams that have a lot of suspended load in them. As they enter the sea, they deposit those sediment loads, and so the river just keeps building more river channel out into the sea. We're going to see that this structure that it creates can resemble kind of like a bird foot. A great example of that is and one that we're going to see here in just a moment, is the Mississippi River Delta. Wave-dominated deltas are deltas that are dominated by are primarily shaped by ocean dynamics. That is, wave energy out in the ocean takes a lot of the sediments that would be otherwise delivered by the rivers and moves them away from the river mouth, leaving behind this kind of triangular shaped area that is the namesake for a delta. That is delta. That is the symbol. The Greek symbol for delta is a triangle. You may have seen that in the past. And a great example of a true wave-dominated delta is the Nile River. And we're going to see a picture of that here in a minute too. In areas where tides rise and fall quite a bit through the day, that's a large volume of water that can move into and out of a river mouth. And in that motion into and out of the river mouth, the sediments that are dropped by the river can be reoriented such that they are parallel to that tidal water movement. So what we'll see in these tide-dominated deltas, we'll see one of these as well, is a series of islands or sediment deposits that run parallel to the direction of the stream. And that's, again, because water from the ocean during high tide goes rushing into the river and distributes sediment in a course that's parallel to that movement direction, that increase in sea level, moving that water into the river mouth. And then during low tide, when the water levels drop, that water moving out away from the river, again, reshapes those sediments into these elongate forms, roughly parallel to the direction of the rise and fall of that water, and that water rushing inland and out of land as a result. So here's a bird foot delta. This is the Mississippi River Delta. And again, here, let's take a bit of a higher look at this delta. What we see here is the existing river delta here for the Mississippi River. The Mississippi River carries with it an enormous volume of sediment. As it enters into the Gulf of Mexico there, it's forced to slow down and deposit that sediment. And in depositing that sediment, right, it extends that river channel all the way out into the sea and continues to do so. The current location of the Mississippi River Delta, however, is not the location that has always been where the Mississippi River enters into the Gulf of Mexico. What you're seeing here is that the Mississippi River, through time, in these portions of Louisiana, have fanned out and made all of these deposits in this area. So these deposits, all of this land that you're seeing here, consists of loose sediments deposited through huge amounts of time by the Mississippi River. As this birdfoot delta has migrated its way east and west, entering into the Gulf of Mexico at this location. Essentially like a train laying down its own tracks and then driving across it. That's what's going on with our Mississippi River. Mississippi River lays down sediments and then flows across it, lays down more sediments and flows across it. So many sediments, and there's so much sediment, in fact, that the weight of these sediments actually takes and bears down on the crust of the earth and actually deflects it downwards a little bit. That's called isostatic loading. Isostatic loading. So huge amount of material here being deposited by the Mississippi River in this birdfoot type delta. Here is our true delta, our wave-dominated delta. This is the north end of the Nile River, and you see this delta has this fan shape. You also see how abundant vegetation is in this area. Life thrives around fresh water, no doubt about it. Terrestrial life thrives around fresh water. And as that river feeds these plants and things that are in this area, the nutrients and sediments that the river brings too helps to fertilize this area. So seeing this fertile block of land here in this triangular shape, again, demonstrating this is demonstrating our wave-dominated delta, this triangular shape that gives deltas their name. Here's a tidally dominated delta system. We've got rivers again entering into the sea. They're depositing these sediments, but the sea level with high and low tide fluctuates so much throughout the day that those sediments are redistributed in these forms that again are parallel to the course of the river system. So seeing these elongate islands again, the river wants to just fill this entire thing with sediments here, but the rising and falling of our tides takes and redistributes those. All right, so that's deltas. Let's talk about some flooding. With rivers comes floods, and here in California, we most certainly experience some significant flooding. There's some amazing photographs that have been taken through the years of significant flooding in our area. We don't get as much flooding as we used to, and that's mostly because we've installed all sorts of civil infrastructure to mitigate flooding, to get water as it falls off of land as fast as possible, or control it in basins as best as we can so it doesn't flood those areas where we work and where we live and where we go to school. But with rivers comes floods. And floods, again, generally associated with periods of extremely high precipitation. And there are multiple types of floods. The first, regional floods, large area flooding. This is large area flooding. Regional flooding can occur far away from where the rain is falling. Again, because of stream capture, or because of how far a river may travel, areas where it might be nice out, right? You might experience the swelling of a river and the eventual flooding of that river and the surrounding areas. That's what we would call a regional flood. Here in Riverside County, we experience, in San Bernardino County, we experience occasional flash flooding. Flash flooding is localized flooding, usually due to storms. So usually around summertime, maybe through the fall, every now and again, we get these big storms that originate as moisture coming out of the Gulf of California. Throughout a really hot day during the summertime, you might look over the San Bernardino Mountains and start to see a small cloud just grow and grow throughout the day to form an eventual big, large thunderhead. And then all of a sudden, your phone starts going off with alerts of flash flooding, or on the TV, you get interrupted by the flash flood warnings, right? And that's because those big thunderheads can sometimes collapse really suddenly and drop a lot of precipitation very fast and overwhelm all of those storm control systems that we have and fill areas with water that otherwise would not be. That is an example of a flash flood, and those warnings are very real. Flash flood warnings are not to be taken lightly. If you receive those warnings, you want to make sure that you're staying out of stream channels or dry riverbeds, because those things can turn on a dime. Those conditions can go south really, really fast. You can also get flash flooding by failure of civil infrastructure. Things like dam failures can absolutely cause flash flooding. Ice jams can cause, or breaking down of ice jams can cause flash flooding. But again, flash flooding, a sudden event, usually local in nature and oftentimes related to storms. I remember when I was a kid, I heard stories about the 100-year flood, the 200-year flood, the 500-year flood. And I would think, wow, every time I tune into the weather, it seems like they can't predict whether it's going to be sunny or rainy next week. But they're telling me that they can predict a flood 100 years out. I don't buy it. And I still don't buy it, because that's not accurate. When you hear about a 100-year flood or a 100-year storm, what they're referencing is not a storm that happens every 100 years. but rather what's called the storm or flood recurrence interval. So the recurrence interval, and what that describes is the probability of a certain size of storm. So people that study precipitation patterns, hydrologists, as they may be called, they'll go through historical accounts and data that they've collected over the years, and they'll compile that in their computer models to look at the size of storms for a given area, for a given drainage basin through time. And what they'll say is that, well, every year we can reasonably expect a storm of this size. Every 5 years, sometimes at some point in any 5-year window, we can expect a slightly larger storm. At some point within a 10-year window, a slightly larger storm, and so on and so forth. So what a 100-year flood or a 100-year storm represents is a storm that each year has a 1 in 100 chance of occurring. So over the course of 100 years, we can reasonably expect that a large storm of a specified magnitude is going to occur, right? But every year within that 100-year window has an equal chance of having that storm occur. So this year, right? This year, we have a 1 in 100 chance of a 100-year storm occurring. We also have a 1 in 500-year chance, or 1 in 500 chance of a 500-year storm occurring. We have a 1 in 1,000 chance of a 1,000-year storm occurring. And again, that's going to be the biggest storm that we could expect over a 1,000-year interval. That's all that we're specifying there is, again, not the frequency, but rather the probability of a certain size storm occurring. That's what that 100-year storm refers to, or that 100-year flood, right? Is the likelihood of that event occurring rather than its actual frequency of occurrence, okay? So a lot of what we do for flood control, that's the construction of things like dams and levees or channelizing rivers or managing or choosing where we can or can't build. A lot of that depends on these assessments on the recurrence interval of different storms, the different size storms that we can expect for a given area. And oftentimes these bits of infrastructure are designed, they're specified, the size of a basin that's designed to collect stormwater may be designed to collect stormwater during a 500-year event. So if you were a hydrologist, something that you might do is, again, look at the computer models to see, well, how much rain falls in a 500-year storm, right? How much rain actually comes to the ground during that event. You're going to take that information and you're going to plug that into your computer software that has all of the landscape plugged into it and everything else. And you're going to make an artificial rainstorm of that size. And you're going to see, well, what's the discharge of the streams during those events? So how big do I need to design my drainage basin to be, or my channels to be? How wide do those need to be? A lot of that is dependent on the calculation of what size of storm, what's the 100-year storm or the 500-year storm, what's the actual size of that event, all right? And then ultimately what you might come up with is we can't control this size of storm given the design parameters that we have, right? I can't build a basin big enough to contain all of this flow that would be needed to keep people in this area safe. At which point, city planners and regulators may decide, well, then we shouldn't build in this area at all. We shouldn't build in this area at all. That's what we call management, right? That's management. So passing no building laws most certainly is part of flood control. Here in the Inland Empire, you take a drive down the 91 freeway and you drive by the Prado dams. And you might see that older dam there. I remember that when I was a kid with the bicentennial painted on the face of the dam. That dam was installed in response to a huge amount of flooding that occurred in Orange County many decades ago. That dam was designed for a specific type storm that decades later, city engineers, hydrologists determined was insufficient to keep people in Orange County from experiencing a significant flood like that again. So what they did, they installed a new dam, and that new dam is off there to the northwest of the existing dam, and it's about 30 feet taller than that bicentennial dam. And that's because, again, they revised the size storm that they were designing to in order to keep people safe. That's what they were up to. Pretty interesting stuff. It's awesome. All right. So in these environments, how does flooding occur, right? If in the city, is flooding any different than it is out maybe in more rural settings? It is. It is. And that's because nature has a great way of mitigating flooding, and that is through vegetation. Vegetation plays a huge role in mitigating the significance of flooding. So in general, rural areas with less development experience less severe flooding than urban environments where there's lots of development. In urban environments, flooding tends to be much more severe. And a lot of that has to do with the lag time of flooding between when the precipitation event happens that causes that flooding, right? So that time from when that precipitation happens to the time of flooding in a rural setting is much longer than it is in an urban setting. And let's take a look at that. Let's take a look at that. So in these two images, again, from your textbook, I wanted to make sure that everybody had this. In these two images, we see the same rain event, and that's these boxes right here, okay? That's these boxes right here. These are the precipitation events. So we got lots of rain. It kind of weakened, and then it strengthened a little bit, and then it stopped, right? So same in both cases. So the center of that precipitation event is in the same place in both of these boxes. But notice that rainfall, right, when it starts to run off, so the stream flow here, right, the stream flow is noted in this light blue curve here. Look what happens here. In a rural setting, right, what we get is that stream flow slowly picks up, then reaches its maximum discharge and then tapers off. And look at the lag time from that maximum discharge to the center of mass rainfall. It's pretty long compared to our urban flooding, where we get that precipitation and the stream flow picks up really fast, really fast. So this curve, the area below these two curves is the same. It's the same volume of water that is moving. However, that volume of water in our urban situation is moving over a much more condensed time interval, which means that the discharge of these streams is going to be much higher, which results in streams potentially overflowing and flooding. It increases the erosive capacity of streams. It also increases the competence of these streams, which can, again, increase the erosional capabilities of a stream. So why is that? Why are cities getting picked on by streams, right? Why does a rural setting do much better in these events? Well, again, it's because of things like vegetation. In an urban setting, those developments create a lot of impervious surface. That is, water falls on the asphalt, it falls on the concrete, and it flows very quickly. It flows very quickly to stream channels that are oftentimes concrete lined. And those stream channels, they fill very quickly as a result, and thus can produce flooding because they lack the volume that's needed to contain all of that water. Whereas in a rural setting, the movement of that water is slowed by vegetation that is present in the landscape. The trees and the plants, the water moving across that surface is slowed down by those items. And so while the same volume of water eventually reaches those streams, it does so over a more spread out interval. This is something that's really being recognized today. And so what we're seeing is a lot of taking of what we had installed previously as stormwater control mechanisms and returning them to a natural or more rural state. We're seeing that in places like the LA River as they take concrete out of the LA River and they're starting to replace that with vegetation. We're seeing that with parks and things installed, green belts installed to try to, again, slow that water down because of this observation. Because ultimately, we're going to have to deal with that same volume of water, but it's much more easily dealt with if we spread that out over a wider area. So it's really interesting once you kind of get the search image for these new, somewhat natural looking mitigation methods or measures. You see them all around. You see them in the parks. You see them in the walkways. You see them in parking lots. They're all over the place. And really the goal there is to try best we can to return these developed areas to a rural setting while still being able to use them for those things that we need to maintain our standard of living. All right. All right. I want to point out one bad place to be in a flood, and those are slot canyons. Slot canyons, these really narrow canyons, oftentimes these things start out as cracks or faults in rocks, that water falling on these faults or cracks in these rocks erodes away those materials present within them and cuts these really narrow slots. These things are so narrow, again, discharge is going to be what it's going to be based on the volume of water that's moving through these areas, right? So the amount of water moving through this slot canyon, right, can be the same as the volume of water that's in a much wider river channel. However, it's just like putting your finger over the nozzle of a hose. When you do that, that water is going to deepen and it's going to speed up quite a bit. And so in these slot canyons, if it's raining, it doesn't even have to be raining at the slot canyon. If it's raining within the drainage basin that is served by this slot canyon, these things can fill up with water really rapidly, and that water can get moving really fast, really, really fast. And so definitely not a place to be during a rainstorm, even if a rainstorm isn't right where you're at. If there's a rainstorm in the drainage basin, you're getting those flash flooding warnings, or you're at all concerned about potential flash flood, this is not the place to be in a flood. People lose their lives in flash floods, getting caught in slot canyons all the time. And so you want to be really careful. So how do we reduce the risk of urban flooding? How do we do that? How do we reduce the risk? Well, again, the installation of green belts, right? That is, install parks and things that have vegetation that's going to help slow that water down, right? Another thing we can do is allow these rivers to act naturally. That is, leave space. Don't build on the river, right? Leave space for that river to meander and cut and do its sorts of things so that, again, nature can do its thing and we just sort of stand back and out of its way. Green belts can also be developed as parks, right? Parks are really commonly included in them, a number of stormwater controls. And again, you'll see them, you might think, well, why did they put this big dip in the park right here? That doesn't make any sense. I'd like to be able to play soccer here, but there's this big hole in the park. What's that about? That's likely to do with some sort of stormwater control to reduce the chance of flooding. Another thing we can do is channelize the water. That is, take the stream, concrete line it, right? Put hardscaping around it and direct that flow right to the ocean. This is what was really popular a few decades ago. It's what was performed for portions of the Santa Ana River and the LA River, especially in the wake of some significant flooding, was if we take the stream and we straighten it, right? If we straighten its course, effectively what you end up doing is you steepen its gradient, right? So if you have a river that's very windy, remember that gradient, to calculate gradient, that's rise over run, right? Rise over run. And so if you calculate the gradient of a stream that winds back and forth, that gradient is going to be really low, right? Really low gradient. And in low gradients, or with the low gradient, that water is going to have to take a really long course to get to the ocean. But what you really want is to get the ocean, or to get the water off of the land. So one way to do that is you steepen the gradient by taking those bends in the river and you straighten them out. You take that denominator in that rise over run, right? And you lower that denominator. You make the run shorter by making it straight. So the water in that river will flow faster. And so you line that river then, that straightened out course in the river, you line it with concrete so that it really moves fast out into the ocean. This was a really popular engineering option for controlling our rivers, but has lost favor for a number of reasons. One, there are more natural alternatives for mitigating flooding without having to spend a ton of money on things like concrete channelizing rivers and losing the ecosystems that come with ecosystems, or as ecosystems as a result of losing these rivers. By covering them in concrete, right? So a lot of the birds and the trees and those sorts of things, they can't set up shop on a concrete lined river, right? So you lose those as well. You also lose the water. We know how precious of a resource water is in this state. And so you lose the water by putting it out in the ocean very fast. So it doesn't allow that water to infiltrate into the aquifers or fill our reservoirs. It just gets rid of it, puts it out in the ocean. So channelization is something that has lost favor. We still see it, certainly, and it's still something that is utilized to help with stormwater control, but it's something that in terms of continuing dealing with flooding is an alternative that's certainly lost favor. Last option, move, right? And that's becoming the case for people as rivers have moved and continually flood areas, maybe even areas that didn't experience flooding in the past are now experiencing flooding. People are being forced to uproot and move as a last alternative. You can't be there anymore. Those spaces are now lost, right? So any of these alternatives and many, many more, it's really an opportunity to get creative here in dealing with flooding. Tons of amazing science still being done in the field of hydrology and mitigating some of these hazards. And I just thought that this was huge. There's some suburban flooding. I know it's cheesy, but I'm trying my best. Maybe some of you got a chuckle out of that. I hope so. That's a Suburban. For those that don't know, that's the name of that vehicle. So anyways, it's never good to have to explain jokes. But in any event, all right, rivers are powerful. They're dynamic, right? These landscapes are also dynamic and they're very diverse. And they're also areas that are potentially susceptible to some very real hazards. So combating flooding in rivers and erosion from rivers, that can be difficult, but it's also an opportunity, right? It's an opportunity to take science and inject it into our lives and help improve our well-being. All right. All right. So with that said, that concludes our rivers and floods discussion. Always a blast getting to chat with you all. Thank you so much for being here. I hope everybody has a wonderful day, and I look forward to seeing you all again very, very soon. Take care of yourselves. All right.